Welcome back to Dr. Liu's VCE Chemistry channel. Today, we are breaking down equilibrium and rate of reaction from the 2025 NHT Chemistry exam. As I go through this, please feel free to correct me if you find any mistakes. All feedback from teachers, parents, and students is greatly appreciated. While activation energy is chemically a fixed barrier of 140 kilojoules and is independent of the amount of substance reacted, the test question treats it as a scalable cost by calculating the molar activation energy and scaling this value to the required 7.00 moles. The resulting energy is 490 kilojoules, which makes 480 kilojoules, option C, the intended answer. Chemical equilibrium is fundamentally dynamic. Upon reaching equilibrium, the rates of the forward and reverse processes become equal, but remain greater than zero. The equilibrium constant provides a quantitative measure of the yield or extent of the reaction. However, it offers no information regarding the kinetics, or the speed at which the system reaches this state of balance. Nitrogen gas and hydrogen gas react to produce ammonia gas. This reaction is exothermic. The concentration time graph for the reaction is shown here. Chemical equilibrium is dynamic before time T2, where nitrogen and hydrogen react to form ammonia. At time T2, the system undergoes a gradual change in concentration for all species, with H2 and N2 increasing slowly while NH decreases. This gradual change, rather than an instantaneous jump, suggests a temperature change. The resulting backward shift in equilibrium, the decomposition of ammonia, occurs because the forward synthesis is exothermic, meaning the system must have been heated to favor the endothermic reverse reaction. If the volume of the reaction vessel is increased, the concentration of all components would decrease rapidly and instantaneously. This stress would cause the equilibrium to shift backward, to the side with more moles of gas, 4:2. If ammonia gas were removed, its concentration would decrease rapidly and instantaneously. To compensate for the loss of product, the equilibrium would shift forward, causing the concentrations of H2 and N2 to slowly decrease, as they are consumed to synthesize more ammonia. At the initial stage, before equilibrium is established at time 1, the gradual consumption of reactants, H2 and N2, and the formation of product, NH3, indicate that the forward reaction rate is greater than the reverse reaction rate. The reaction quotient, Q, quantifies the extent to which the reaction has proceeded at that moment. Crucially, during this non-equilibrium phase, Q is not equal to the equilibrium constant, K. Furthermore, Q, being a thermodynamic parameter, bears no relation to kinetic factors such as the activation energy or the overall reaction rate. An equilibrium mixture of nitrogen dioxide and dinitrogen tetroxide is present in a vessel. Adding an inert gas at constant volume increases the total pressure, but does not change the partial pressures, or concentrations, of the reacting components. Thus, the forward and reverse reaction rates remain unchanged, and the equilibrium is unaffected. If the concentration of the product, dinitrogen tetroxide, is increased, the rate of the backward reaction increases instantaneously. This causes the concentration of the reactants, NO2, to increase and the concentration of the product, N2O4, to decrease slowly, which in turn causes the rate of the forward reaction to increase until a new equilibrium is established. If the volume of the reaction vessel is increased, the concentrations of all components decrease instantaneously, reducing the rates of both the forward and backward reactions. The equilibrium constant, K, is dependent only on temperature. Since this system is at a constant temperature, K remains unchanged. The equilibrium constant is always independent of the reaction rate. Initially, a sealed container held only carbon dioxide, CO2, and carbon tetrafluoride CF4, with no carbonyl difluoride, COF2, present. The reaction proceeding to equilibrium is: when the system reached equilibrium, the stoichiometry dictates that for every 1 mole of CF4 that reacted, 2 moles of COF2 were produced. Therefore, the equilibrium concentration of COF2 is twice the change in the concentration of CF4 from the initial state. Initially, a sealed container held only carbon dioxide, CO2, and carbon tetrafluoride CF4, with no carbonyl difluoride, COF2, present. When the system reached equilibrium, the stoichiometry dictates that for every 1 mole of CF4 and CO2 consumed, 2 moles of COF2 were produced. Therefore, the equilibrium concentration of COF2 is twice the change in the concentration of CF4 from the initial state, and the change in the concentration of CO2 is equal to the change in the concentration of CF4. Using these stoichiometric relationships, one can calculate the equilibrium concentrations of all components and subsequently determine the equilibrium constant Kc. Since the volume of the reaction vessel is 2.0 L, adding 1 mole of CO2 results in an instantaneous increase in its concentration by the concentrations of the other components, the CF4 and COF2, remain momentarily unchanged. Using these new concentrations, the original equilibrium concentrations plus the instantaneous increase for CO2, we can calculate the reaction quotient, Q, to determine the direction of the new equilibrium shift. After the instantaneous increase in the concentration of CO2, the calculated reaction quotient, Q equals 0.29, is less than the equilibrium constant, Kc equals 0.49. Because Q is less than Kc, the system is not yet at equilibrium, and the reaction will spontaneously shift in the forward direction to consume reactants and produce more product, thereby increasing the yield of COF2. Fundamental concepts: kinetics versus thermodynamics. Activation energy, EA, calculated as 480 kilojoules for the formation of 7 moles SO3, based on 140 kilojoules for 2.00 moles SO3. Dynamic equilibrium. Forward and reverse reaction rates are equal but remain non-zero. Extent versus rate. The equilibrium constant Kc measures the reaction's yield, extent. Kc is a thermodynamic value and is independent of kinetic factors, rate, activation energy, point 2. Le Chatelier's principle, shifts and stresses. Under Le Chatelier's principle, applying stress causes shifts. An increase in temperature, MCQ 6, on the exothermic N2H2NH3 system causes a gradual change and favors the backward, endothermic, reaction. Conversely, adding an inert gas at constant volume has no effect on the equilibrium for the system, as component concentrations are unchanged. Finally, an increase in vessel volume causes an instantaneous decrease in all concentrations, which lowers the rates of both the forward and backward reactions. 7.3. Quantitative analysis, Q versus Kc, stoichiometry. COF2 produced is twice the change in CF4 consumed, equilibrium constant, calculated as 0.49 for the initial conditions. Kc is only dependent on temperature, shift analysis, stress. An additional 1 mole of CO2 is added to a 2.00 L vessel, causing delta CO2 equals 0.50 m. Shift. Since Q is 0.29, Kc 0.49, the reaction spontaneously shifts forward to restore equilibrium, thus increasing the yield of COF2. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.